This is Professor Pelton. This is part 4 of Chapter 1, Section 3. This is just a smorgasbord of problems that involve all the things that we've learned so far as radicals and exponents and simplifying. And these are some numeric and algebraic combinations, so it kind of puts everything together. All right, so the first one is the third root. So third root, we have 64, which is 8 and 8, which is 2, 2, 2, 2, 2. 1, 2, 3. Oh, we're short 1, 2, right? Because that's 8 and 8. And then y to the sixth. Okay, so the exponents I'm not going to write out because that's obnoxious. So I have 3 2's there for 2 to the thirds. That's a 2. I have 3 2's there, which is 2. So using the shortcut rule, this is y to the sixth. So 6 divided by 3 is 2, and there's nothing left over. So this is 4y to the second. So that is a perfect radical. Nothing gets left on the inside. So the numbers you can write out, but the variables you don't need to, just divide, right? So the next one, let's do the fifth root of 4, because 4 is 2 and 2, and the reality is there's not going to be enough, there's not enough 2's there to actually take anything out. Okay, so 8 divided by 5 is 1, right? Whoops, let me rewrite this actually a little bit lower so I have some room. So let's erase this and write it a little bit lower. Okay, so fifth root of 4. Okay, so 8 to the 1. Okay, so, and there's 3 left over, correct? Because 8 divided by 5 is 1 with 3 left over. All right, b to the 14. 14 divided by 5 is 2. And there's 4 left over. And then c to the fifth, 5 divided by 5 is 1. And there's nothing left over. So that's the best we can do on the next one. That's an imperfect one. The first one was perfect. The second one was not perfect. The third one is add and subtract. You cannot add and subtract unless they're like terms. Okay, but this one's algebraic. So 12 third roots of 2, and this would be z to the third, or z squared, minus z third roots of, let's see. So if you think about what 54 is, 54 is really 2 times 27, right? So that's 2, 3, 3, 3, and then z squared, right? Okay, so originally these are add subtract. They're not like terms. You can't add them. But I have a group of 3's here, right? So this is 12z third roots of 2z squared. Not really making good 3's there, but that's okay. And then minus, I have a group of 3's here. So 3z and then third roots of 2z squared left over inside. So now these are like terms. So 12 minus 3 is 9z, third roots of 2z squared. You put a multiply in there if you want to. So now I've done like terms. The first one was a perfect radical. The second was not a perfect radical. And this third one is an add subtract problem, which was not doable until I simplified. Okay, so let's try the next couple. So the next one is a quotient. And I cannot divide 4 by x by y. That's not going to work. But I can certainly use the quotient rule to break them apart separately. So this is the fourth root of x to the fourth over the fourth root of y to the eighth. And we can use our shortcut here instead of writing out 8y's. So 4 divided by 4 is 1. And then 8 divided by 4 is 2. And again, if you need to, you can write them out longhand, but that becomes painful. All right, so if we look at this one, what can we possibly do? Well, reality is nothing. As we rewrite this, this is x to the over y to the 8 thirds. There's not much you can do there, okay? Because there's nothing in common on the top nor the bottom. You're just changing from radical notation to exponent notation, so either one is fine, okay? All right, lastly, 14 divided by 2 is 7, and that's a 1. So this is x1 minus 3/4. And then the y is 1/3 minus 0, because there's no y's in the bottom. And this is z0 minus -6, because there are no z's on the top. There are no z's on the top. there are no y's on the bottom, so just put them in as placeholder values. So 7x to the 1/4, right? Because 1 minus 3/4 is 1/4 times y to the 1/3 times z to the 6th, and that's good enough. You can rewrite them in radical form if you want to. So 7/4 roots of x times the 3rd root of y times z to the 6th. Either one of those is sufficient answers. At that point, it's a matter of what does the question call for? Does it call for exponent or radical notation? It doesn't call for either one in this case, so it's really a preference. All right, try the student problems. Okay, so the 3rd root of 27, so the 3rd root of 27, 27 is 3, 3, and 3. And I'm not going to write all the x's. So that's a group of 3's that comes out. And then 9 divided by 3 is 3. So this is a perfect radical. There's nothing left in the radical under the radical symbol. All right, so the next one, the 4th root of 32. Well, 32 is 4 times 8. So that's 2, 2 is 4, and then 2, 2, 2 is 8. Right, so that is all the multiples to give you 32. A9, B16, C11. Let me fix this line a little bit here. Okay, so I have 4 2's. Okay, and then we'll put a radical symbol. Hopefully I left enough room. Okay, so there's a 2 left over into there. We took out one group of 4. All right, so A9, a to the 9th power. 9 divided by 4 is 2, and there's 1 left over. B16, 16 divided by 4 is 4. There's nothing left over. And then C11, 11 divided by 4 is, excuse me, 2, right? So C to the 2nd. So that's what, 8, and then 3 is left over, C to the 3rd. And that's the best we can do there. Okay, last one is, no, that's not the last one. Adding and subtracting. Those are not like terms. So 3, 3, W5 minus W, W3, right? So a 3 comes out, but remember, this is square root, right? So 5 divided by 2 is 2, and there's 1 left over, right? Right? 5 divided by 2 is 2, 1 left over. Minus 3 divided by 2 is 1, and there is 1 left over. Okay? All right, so this is 3w squared square root of w minus w squared square root of w. So what do I really have? I have 3w squared minus 1w squared is 2w squared square root of w. And you can actually rewrite this problem again if you wanted to. Because the reality is, what is this really? This is 2w squared times w to the 1/2, right? Because if you're writing the radical into an exponent, then I can actually combine these farther, because 2 plus a half is 2.5, correct? So think about what 2.5 is as far as an exponent. That's 5/2, isn't it? So you can actually go even farther if you put it into one notation, which is my recommendation. Don't keep one notation. Don't keep two notations. Keep one. It simplifies better. An exponent is usually the better choice of the two. Okay, lastly, or last line here. This is x divided by y is not possible, but I can break this apart using the, whoops, I wrote the wrong thing. I can break this apart using the quotient rule of radicals and get x10 on the top and y5 on the bottom. Okay, so 10 divided by 5 is 2, and 5 divided by 5 is 1. So that completely simplifies, or it's a perfect radical. Okay. So this one, you can do the division thing we just did, or you can simply rewrite it in exponent notation. So it's x over y to the 10 over 4, or x over 10 fourths is really 5/2. Okay. All right. And then f, 6 divided by 3 is 2. Then I have x to the 1 minus 1/2, because there's really a 1 here as a placeholder value. And then y to the 3/4 minus 1/2. So you have 2x to the 1/2, and then y to the 1/4, right? 3/4 minus 1/2 is 1/4. And you can rewrite that in radical notation if you want, or keep it in exponent notation. Okay. So knowing we can go back and forth between notations, I want to revisit like radicals or simply like terms when adding. Okay. So essentially, when they say like terms, it's the same product. So these have to be the same radical, right? Whether it's square root, third root, fourth root, so and whatever the case may be, then you can add the constants, which is what we've been doing. So that works in both notations, right? So for example, this is 1/4 root of 10 and 7/4 roots of 10. So 8/4 roots of 10. So another perspective is this is really 1 times 10 to the 1/4 plus 7 times 10 to the 1/4. Right? Which gives you 8 times 10 to the 1/4. So these are equivalent answers. Okay. So likewise, if I gave it originally in the radical or the exponent form, these are in fact like terms. This is 12 times 8 to the 1/5. Or if I rewrite the problem, this is 2 times the 5th root of 8 plus the 10 times the 5th root of 8, which 10 and 2 give me 12 5th roots and 8. So those are equivalent, right? So I'm trying to connect what we've done so far all together with adding and subtracting, because there's essentially only one rule for adding and subtracting, right? If they are like terms, add or subtract the constants in front. Just keep the products as is, right? All right, pause the video, try the student problems for yourself. Okay, so for the student problems, 7 minus 1 is 6 5th roots of 12. And then 4 plus 8 is 12, 9 to the 2/3. Or if you want to rewrite it, 12 third roots of 9 to the second power, right? And you can put that second power on the inside or the outside. I like putting it on the inside when I'm showing it, or outside when I'm calculating, to be honest with you. All right, that is the end of part 4.